We now look at the concept of entropy, and entropy is very important when dealing with thermodynamics. So entropy is a measure of how much energy is not available to do work. The larger entropy is in a system, entropy is often represented by the letter S. The more entropy a system has, the less work you can get out of that system. So entropy changes during processes. Change in entropy for a reversible process is given by the equation. The change of entropy is equal to the heat transferred during that process over the change in temperature. Now, the total change in entropy for a system that undergoes a reversible process is 0. And as a reminder, a reversible process is a process where you go from one state to another. By undoing what you just did, you can get back to that initial state. So there's a clear forwards and backwards that can occur, even spontaneously, in a reversible process. During a reversible process, entropy does not change. However, most processes, especially the ones we deal with on an everyday basis, are not reversible, they're irreversible. And during an irreversible process, again, perfume getting into the air in this room is an irreversible process because the perfume will never spontaneously all gather back together and go back into the bottle. Right? Humpty Dumpty sat on a wall, right? All the king's horses and all the king's men couldn't put Humpty back together again. So break an egg, you cannot unbreak that egg by changing its elevation. If you drop an egg and it breaks, you can't just raise that broken egg back up and expect it to repair itself. Baking cookies, right, is an irreversible process. You heat up cookie dough, you end up with cookies. You cool down those cookies, you don't get cookie dough again. So entropy increases for closed systems undergoing irreversible processes. And I did add closed systems, which your book doesn't really talk about, because there's a common misconception with the concept of entropy, that entropy can never decrease, that entropy always has to increase. And for closed systems, it does. But, for instance, you are not a closed system. You start off as a single cell, but now you're the trillions of cells sitting here watching this video. That is a reverse of entropy. You went from a disordered or low energy state to a very ordered system. But you took in a lot of energy. You ate, right, during this process. The Earth, one of the arguments, incorrect arguments against the idea of evolution, stems from the second law of thermodynamics. Ignorant people will say, well, you can't have evolution. You can't go from simple life forms to complex life forms because that violates the second law of thermodynamics. And if Earth was a closed system, that would be true. But Earth is not a closed system. It's being dumped, energy is being dumped on it from the sun. Tremendous amounts of energy is being dumped on the Earth from the sun. Now the Earth-Sun you can think of that as a closed system, and that entropy is increasing inside the sun. Energy is going from a highly ordered state to a disordered state inside the sun. More of the sun's energy every second is becoming less available to do work, therefore the entropy is increasing. So the total entropy of a closed system never decreases. If the processes are reversible, it can stay 0. If the processes are irreversible, entropy will increase, but the entropy never, ever decreases. Entropy is also a measure of the disorder of the system. So we'll look at entropy from a statistical standpoint in the next video. But right now I want to talk about what does this mean about change in entropy. It just means that over the long term, very long term, billions and billions of years, energy in the universe will come into less and less useful states. Nuclear energy is energy, in the nucleus of an atom. You can use nuclear power to, generate motion, generate electricity. But in the end result, you always get heat out. You always get heat in this transfer of, every time you make a transfer from one energy bank account to another, chemical energy to kinetic energy, or nuclear energy to thermal energy, you always end up with that extra little bit of thermal energy, that heat, waste energy, right? Your automobile. When you're driving, you're turning chemical energy of the gasoline into motion of the car, but at the end of the day, you park your car. Where did all that energy go? It went into heat the disc brakes. It went into the air resistance, heating up the air that you drove through. It went into the friction of the tires on the road and so on. So you lose that nicely ordered chemical energy, becomes wasted heat energy. And over the very long time, energy in the universe cannot be regained. It cannot go back to an earlier useful state. So physicists and astronomers talk about the heat death of the universe. That in a very, 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 very long time in the future, all of the energy is basically going to be thermal energy in the universe. There won't be any gravitational potential energy left. There won't be any chemical energy, nuclear energy, and so on. The universe is just going to be a sea of these weakly interacting particles that are moving about at some high kinetic energy. Therefore, it's just temperature. And since the universe will be on the large scale uniform, there's no temperature difference for you to power a heat engine from. So we end up with the universe dying what's called the heat death. That is very, very Google years in the future, right? Nothing we have to worry about today. The sun is going to be around for over 4 billion years. We have plenty of energy that we can use. So we'll look at entropy. And entropy can be thought of also as a state of disorder of the system, right? Irreversible processes cause disorder. An example you might be familiar with is your bedroom, right? Or your bedroom or your house or your apartment, wherever you live. Over time, entropy takes over and you get disorder, right? You get clothes on the floor, dirty dishes, dust on things, books not put back, toys laid out, whatever. How do you reverse entropy in that system? You put energy into that system. You do work, right? You clean up, you dust, you wash dishes to get that system back to where it was, but you had to put energy into that system to fix it. So entropy can be thought of as a state of disorder, and we'll look at entropy from a statistical standpoint in just a moment.